This is the talk through the chapter 7 homework. We did number 8 in class, so we're going to begin with number 10. And I'm going to begin by writing down what we know. So we have a metal and we have a sample of water, and we want to bring them to the same temperature. So the metal has a mass of 1,230 grams. This will be the metal data. We know for the metal that the specific heat capacity is 0.449. It tells you that in the diagram, so you have to look at the diagram. We don't know the, actually we do know. We know the beginning temperature of the metal. We know Ti. So back up here, be a little more, it's early in the morning, so I'll get better as we go. So we got mass is 1,230 grams. We know the Cp is that number. The Ti is equal to 68.5. You have to go back to the problem to find that. So 68.5 degrees C. And T final is 25.6. All right, for the water, you don't know the mass. You do know the specific heat capacity of water. It's 1 calorie per gram degree C, but it takes 1 calorie is 4.18 joules, and we most often will use joules. So 4.18 joules per gram degree C, which means it takes 4.18 joules of energy to raise 1 gram by 1 degree. Ti of the water is 18.5, and T final will be the same as the metal. And so when you put the metal in the water, you know that the metal's temperature is going to go down to 25.6. You know the water's temperature is going to go up to 25.6. What you're looking for is the quantity of water that you need. And they ask for it in milliliters, but first you must find it in grams. So we know that the quantity of heat lost by the metal is equal to the quantity of heat gained by the water. So the mass times the specific heat capacity times the change in temperature of the metal equals the mass times the specific heat capacity times the change in temperature of the water. All you need to do then is find the mass, because you know everything else that you need in order to find what the mass of the water is. After you know the mass of the water, you know that 1 gram is 1 milliliter, so just change to milliliters. So that was number 10. Number 13. Number 13, you've got a chemical reaction. This is just a stoichiometry problem. You know that you've got calcium oxide reacting with water to make calcium hydroxide. And we also know that there are 65.2 kilojoules of energy released. That's the change in enthalpy. We talked last class about what enthalpy is. Enthalpy is essentially heat change, ignoring, there could be pressure volume work, but we usually ignore the pressure volume work, especially in this case because there won't be any gas produced here, so there won't be any pressure volume work. So delta H is 65.2, but it's negative. Does that mean energy's in or energy's out? So that would be energy out. So then you just have a stoichiometry problem. Change to moles. Then the mole ratio. Okay. Actually, you don't have to do, rephrase that one. So if you change, all you really have to do is change to moles. of calcium hydroxide. So grams to moles of calcium hydroxide. This many kilojoules is the energy change for this equation as written. So this many kilojoules, and listen carefully, in this case is equal to that, or that, or that. In other words, if I were to react 1 mole of calcium oxide to make calcium hydroxide, I would require 65.2 kilojoules of energy would be released. If I were to react 1 mole of water, 65.2 kilojoules would be released. And if I form 1 mole of calcium hydroxide, 65.2 kilojoules of energy are released. So this number applies to the given quantity of anything in the equation. That when I say given quantity, I mean the stoichiometric quantity. So if there had been a 2 over here, then this would have applied to 2 moles of water. Okay, so this is actually a very straightforward question. You know how many moles of calcium hydroxide, you know that this many kilojoules per mole, and then you make that, you just multiply whatever the moles are by 65.2 kilojoules per mole, and you have the number of kilojoules. So the next question is number 14. Okay, so here we go with 14. In 14, we're going to burn a hydrocarbon. It's C8H18. So C8H18. When we burn a hydrocarbon, we combine it with oxygen. The products are always the same when you burn a hydrocarbon, CO2 and H2O. All right, so if I balance the equation, I get an 8 there. I'll have a 9 here. Oops. Okay, so where was I? An 8 here, a 9 there. That would give us a total of 16, and 9 is 25 oxygens. So that doesn't work very well because 25 oxygens is an odd number, and I can only have an even number on this side. So in that scenario, what you need to do is go back to the beginning and double this. That means we're going to have a 16 here, and we have 36 hydrogens, so we'd have an 18 here. 32, 16 times 2 is 32, 18 times 1 is 18, so you have 50 oxygens on the right side, so you have 25 on the left side. So there's a balanced chemical equation. And we also know the heat of combustion. The heat of combustion that's given to us, I'm going to put a COMB there and there for combustion. The heat of combustion is 5,480 kilojoules per mole. So the 5,480 is negative because you're burning something, and I think you know that when you burn something, energy is released. Now that's per mole. So in this case, how many moles do we have? So the stoichiometric quantity is 2. So that means if it's in this particular reaction, as we have written it, this 5,480 kilojoules per mole is going to need to be doubled, because there's a 2 in front of the octane, and this is per 1 mole, so it'd be 10,960. So for this particular reaction, delta H equals 10,960. Often, you'll see this reaction written with a 1 here, with a 13.5 here, or 25 halves here, and an 8 and a 9. And the reason for that, if you write it like this, then you have 1 mole, so this number that's on the standard tables of heats of combustion of different compounds will apply for the equation as you wrote it. That's why you see halves sometimes in balanced chemical equations. All right, so 10,960 is the energy we're going to use for every 2 moles of octane. And we want to know how much is liberated per gallon. So if we have a gallon of octane, we're going to burn it. We want to know how much is released. Whoops, gallon has an N right there. All right, so we need to change gallons into some other unit. And I think they gave us some information here that 3.785 liters is a gallon. So 3.785 liters is 1 gallon. They gave us a density of 0.703 grams per milliliter. So since we're dealing with liters here, I mean, you could change them. You want to change the milliliters first, just keep it straightforward. So milliliters, liters. 1,000 milliliters is 1 liter. Milliliters here. Now I forgot what I said it was. 0.703 grams. So 0.703 grams. All right, so at that point you'd have your grams of octane. So then you change your grams into moles. And then you know that there are 10,960 kilojoules for every 2 moles. And why is it 2 moles? Remember the 2 in front of the octane over here? All right, that should give you the correct answer. So that was number 14. Number 21A. Okay, so 21A is another stoichiometry sort of kind of questions. So you've got 0.205 grams of potassium hydroxide added to water in a styrofoam coffee cup. So we know that the potassium hydroxide, when you put it in water, will dissolve. Since potassium hydroxide is ionic, when it dissolves, it turns into K plus and OH minus. So we're really measuring what's called the heat of solution here. We know that we're putting it in a styrofoam coffee cup. So we'll draw a quick picture, high quality drawing of a coffee cup right here. Whoops, that's not such a good drawing. Let's try it again. So a little drawing right here of a coffee cup. That's very accurate looking. Okay, so we put the potassium hydroxide into the water. The water, of course, is going to have its temperature go, up or down? It says it rises. Okay, so we want to know what is the approximate heat of solution in kilojoules per mole. Well, we know the quantity of heat of the water is a mass times the specific heat capacity times the change in temperature. So you could find the heat gained by the water. So find Q. Okay, this will be for the amount. This is Q for the, how many grams did we use? 0.205 grams of potassium hydroxide. So that's Q for the 0.205 grams of potassium hydroxide. So once you know the Q for the 0.205, I'm going to go back over here because I'm out of room on this page. Change that into moles. Okay, after you know the moles of KOH, the Q is equal to whatever moles you have of KOH from right here. We want to know it in joules per 1 mole, but all you have to do then to find that is the joules. So divide joules by moles, and that'll give you in joules per mole, then convert that to kilojoules per mole. The way you would do that is, there's 1,000 joules in a kilojoule, so you divide by 1,000. So let's run through that again. We're putting potassium hydroxide in water. It's going to dissolve. It's going to make the water get warmer. So you use this formula to find the change in heat of the water. we know that was all caused by the 0.205 grams of potassium hydroxide. So now you change your 0.205 to moles, okay, and then divide the Q, which was in joules, divide it by the number of moles of potassium hydroxide that you had right here. So that would give you joules per mole, then convert that to kilojoules per mole. Okay, so when I do that dilute thing, did I erase anything you need to know? I don't think so. All right, so there you go. So joules per mole, then change that to kilojoules per mole. All right, that was number 21A. I'm going to stop there because I'm out of room on this page, and I'll come back with another page.